CSA giving us a talk on density, neglected but essential. And we have three speakers, Andrew Scoggings, Bill Shaw and Grant Louw. And before we get started, we should also remember that, or I should let you know that they've sponsored drinks tonight, so it's when they're finished, they deserve an extra round of applause. Yes. Because there's not many in this current climate that are helping us out like that. So the talk tonight has four parts. What is bulk density, which Andrew is going to deliver, QA, QC and JORC requirements, which Bill is going to deliver, methods and examples, and Grant is going to finish off with the correct calculation of volumes. Just a little bio on these guys. Andrew Scoggings graduated as a geologist in the 1970s and started his career in underground copper mines in Zimbabwe before he went off to work on the deep level Witwatersrand gold mines. In the late 1980s, Andrew completed his PhD research on alkaline granitoid nepheline cyanide complexes in South Africa, and it was here that he got introduced to industrial minerals. Andrew worked as a geologist and marketing manager for GW Industrial Minerals before he moved to Australia in 2001, where he commenced working with Amcoal International, managing Louw and chromite exploration activities. Andrew is a principal consultant at CSA Global and is a regular contributor to Industrial Minerals magazine. His on the requirements of JORC 2012 Clause 49, highlighting the need to report industrial minerals resources according to market specifications. Andrew is a registered professional geologist specialising in industrial minerals. The second speaker is Dr. Bill Shaw. Many of you probably know Bill. He's had extensive experience in economic geology and mining, with operational experience in gold and ferrous metals. He's lived and worked in Chile and Canada and has signed off on mineral resources and ore reserves for many commodities as a competent person. He is an internationally recognised consultant with over 40 years' experience in the mining industry and has specialised in auditing, grade control and reconciliation for many years. Bill also has a number of voluntary roles, including residing on the Joint Ore Reserves Committee and the Valmin Committee, and he's currently the President of the Australian Geoscience Council, the peak body representing all geoscience in Australia. The third speaker is Grant Louw. Grant graduated as a geologist from the University of Pretoria in the 1990s and started his career as a geological information officer with Anglo American in Johannesburg, before starting work as a mine geologist in the Consolidated Murchison Antimony gold mine in Gravelite, South Africa. I hope I got that right. After spending a few years as a freelance geologist, Grant moved to Australia to join CSA Global in 2006, where he's now employed as a senior resource geologist. A diverse range of commodities including iron, gold, base metals, mineral sands and graphite. And his main focus at CSA has been modelling and resource estimation in the gold and iron ore sectors. Sorry about that. That's our speakers, and I'll now get Andrew to come up and commence the talk.
Glenn, thank you very much for that introduction, and thanks to MEGWA for the opportunity of presenting this topic to you this evening. Hopefully it's not too boring. I know density sounds like one of those real mundane sort of things, but it's actually quite fun. Okay, the poor orphan and mineral resource estimation. Just to set the scene of where we're going tonight, presentation outline. What is bulk density? That's me giving a very brief description, followed by QA, QC and JORC requirements by Bill, method examples, myself. Grant is going to show us some interesting information on how to measure volumes on half core, and conclusions by Bill. This one, underestimation of density will have consequences. And this is, I'm going to show you two slides that kind of piqued my interest in density. This was in China at a clay mine, and clearly this bloke hadn't worked out how dense bentonite clay was, and he'd even added extra bits of wood to the side there to put more in with dire consequences. Another one, also in the clay industry, these guys that I was working with said we always get out more than we thought that was in the resource. Well, interestingly enough, they've been using 1.45 tonnes a cubic metre, or 90 pounds. We went and tested some clays in Turkey and Australia and came out with that density of around 1.7 to 1.8. These are with about 25% moisture. So there's a difference of 24%, so no matter, they always got out more than they thought was there, so there was a lot of slack in the system. That was a conservative density. It could also go the other way, optimistic, and get the density higher and come up with more tonnes than should have been there. So these two things kind of got me interested. So bulk density, what is it? This is an example from Oz in monograph 30. We've taken the table from Lipton and Horton and made a few modifications, so we don't need to go into a huge amount of detail. But the first thing to point out would be that specific gravity is relative density, and the ratio of the density of that material to the water at 4 degrees, and it doesn't have any units. Then we have some categories of density in these other 4 rows. Basically density being tonnes per cubic metre, or the relationship between mass and unit volume. In situ bulk density, which is the density of the material with its moisture content. In situ dry bulk density, which would normally be used in the metals industry where the assays are done on dry samples. And then loose bulk density, where there's a swell factor where there may, for example, on a stockpile. So we'll give you a few examples from some of those as we go through it. Now, why do we measure it? Again, no rocket science, you all know this, but it's good just to remind ourselves. There are 3 fundamental inputs to a mineral resource: grade, volume, and density, and we need the density to multiply by the volume to get the tonnes. Now there are 3 components in density. Mass, this is usually the easy piece, easy to weigh something generally. However, volume, that's where the difficulties start to arise, and I'm sure we're all very familiar with that. How to get the volume. And then the moisture is something else, and again, with my industrial minerals background, I've often found is inconsistently or not done, where we are mining wet clay, and we need to know the density of that wet clay, because that's what comes up onto the stockpile for drying. And often moisture isn't done properly. And I'd like to now to run through some QA, QC and JORC.
Thanks, Andy. No pockets. So, look, it's our contention that density measurements should be treated exactly the same way as assays. And as you know, with assays, they must be defined and interpolated within consistent domains such as the weathering and the lithology. They need QA defined quality assurance set of procedures, collection documentation, equipment calibration, alternative methods, umpire labs, and they need quality control data. They need standards, duplicates, statistical analysis of precision and accuracy. And this is the part of the JORC code in Table 1 that actually mentions density. And interesting, it only discusses density under mineral resources, not under ore. So bulk density, you have to explain whether it's assumed or determined. If it's assumed, the basis for the assumptions. If it's determined, the method, whether it's wet or dry, frequency, size and representativeness of the samples. And of course these days you have to put all of this in Table 1 with the if not, why not clause under JORC 2012. You have to make sure that the bulk density suitably accounts for the vugs. You have to explain what the moisture is. You have to look at the differences between the ore and the waste, the rock alteration zones. You have to discuss the assumptions that you've made in the density estimates and that you've used to evaluate the different materials in the deposit. Again, the ore and waste, or the different materials that might be going into the mill as part of the ore. So there's clay ore and hard ore, etc. So a lot of the reports that we see, that we review, just very quickly skate over this whole issue of density. And yet, really, it's exactly the same as an assay. There is good grounds for pinging a report if they don't have enough samples, if the samples aren't representative, if they haven't explained where they come from, if they haven't appropriately discussed all the methodology, the results, the assumptions, and the errors that they expect to see, the difference, the pluses and minuses. So density information provided in a public report, similar data analysis and discussion to the assays. And that includes descriptions of the methods, which is the quality assurance, and also for both moisture and for dry bulk density, of the frequency, representativity, accuracy and precision. That's all the QC part of the analysis. And that means perhaps doing things like making sure that your weights, your weighing balance and certified. It's just a small point. It's something that I've not come across before, actually going back, recalibrating a set of scales with standard weights. We all know that the revenue for the project is determined by the ore metal, the ore value, the metal, and the metal is equal to the grade times the volume times the density. So in your densities, if you've got a bias, you can end up with a problem in the whole resource estimation process. The economic value of the project is determined by the revenue minus the costs. And we've seen plenty of examples where the mining cost in open pit projects, largely determined by the cost to move the waste, can be got wrong if the density estimation hasn't been done correctly. And the density should be determined and assigned or interpolated in an unbiased way for both the ore and the waste to ensure that the revenue, the NPV, the dilution are all correctly estimated. So this just a little. We've actually seen a density sampling program done over the ore and the waste, which are the yellow samples here, and they've actually presented their results because they had a big reconciliation issue. Now this is in trying to resolve what's happening on the mine in terms of ore reserves, but it's certainly information that could be reported in a public report to this sort of extent. There are a few things in this presentation. I'm going to talk about the impact of, for instance, nickel grade on the density and how the grade can vary with the density, and how you can apply factors and how those factors can introduce a bias to the estimate of the total metal, not only just through the tonnage but also through the grade. We're not going to talk about the sand replacement method of estimating density. This is something called the Troxler, which is used to estimate density in a lot of civil engineering situations, but can be used for stockpile estimation, just a probe that goes down with a gamma source or a neutron source at the end, and the same with downhole geophysics source used to estimate the density directly. But these methods all have to be calibrated, and they can be a useful check on the other methods that you might be using. So we'll go back to Andrew, who's going to go through some various examples that we've come across.
Thanks, Bill. And one thing I didn't mention right at the beginning is thanks very much to CSA management for the time that Grant and I have spent on preparing this talk. We appreciate the opportunity. Thank you. Right, bulk density. There's a bewildering array of methods which we have all seen before for measuring the volume of a sample. And this could be a core sample, full whole core, half a core, rock samples, stockpiles, powders, and so on. And a couple of the methods. Water displacement. Uncoated for samples that are competent or non-porous. and then if it's a porous sample or something you don't want to get wet, it may have some clay in it that expands. You could seal it with wax, spray lacquer, cling wrap, or vacuum pack. There's a number of different. Caliper, which Grant is going to discuss in a bit more detail, that's the whole or half core. The whole core tray method, pitting, and then the picnometer, which we'll bring up at the end. We have a couple of little case examples, stockpiles and bulk samples, whole core, and then the half core, which Grant will address later. And I'm just going to show you some illustrations of some of these. So stockpiles and bulk samples, this is a really neat example of a pit that's, this cubic meter that's been some a teaspoon or something. Oh no, that's the borehole down there. This is a nickel laterite deposit. They had to build a roof over it. Quite a big business. But just look at how neat and square that is there, and also that they can compare the grade. Very impressive. Here's a slightly more, should I say, more agricultural way of doing things. This is in Queensland. That's a stockpile of bentonite with 10% moisture, but it's effectively dry. We made up a steel box, a metre cubed, filled it up with a front end loader, scraped the top off, then went and weighed it on the scale at the mill and the plant. So that gave us the loose bulk density, brought it back outside, filled it up, and then put it on the forklift, bumped it up and down, got it to settle down, filled it up and weighed it again, and that gave us the tap bulk density. Of course, there's other ways of doing things. One's like survey the whole pile, remove it, weigh it over a weigh bridge, and then work out the volume and do all that, but we didn't have that luxury at that stage. But it worked quite well. Then there's whole core. Sometimes you can be lucky. This is a graphitic gneiss from East Africa. Whole core, nice and competent, easy to do. Easy to do, no problems. You could end up with that, real problematic nickel laterite. What on earth do you do with that or that? So what happened was, let me go and try some of these different methods. And I did this at this chromite mine in South Africa. So I tried the hairspray or lacquer on a quarter core of friable chromatite. That worked pretty well. Tried some beeswax, that's this brown stuff, it melts at about 60. And we tried competent, I had a number of samples, we tried, competent, weathered, and did various methods just to compare them. Paraffin wax is also a very neat method. We use disposable aluminium trays, which are really good, nice and easy to do. That's me putting the friable chromatite into the tray. Of course, a deeper one would be really good with some tongs or something to drop it in. And then a draining tray on the right-hand side just to let the thing dry off and let the material set. Vacuum pack over there, that can work quite well. Something I did find though, if you have sharp edges, it can break the vacuum bag. And then cling wrap that we've all heard about. You can end up with a piece of core like that, and then somebody says cling wrap it with that, and I defy anybody to come up here later and see if they can get it without any air pockets. And caliper method. Not an ideal caliper. I was stuck in a situation where I didn't have a fancy caliper with a digital thing. Went and bought this and tried it out, and it worked quite well. That was what was available at the time. And again, the caliper method, in this case I only had calipers. It was a bentonite mine, and we drilled without water, the core. I then used the hacksaw to trim, got the shavings off the water, and then did the density by the caliper or ruler method on that. And that was that one. And then just to show you some of the examples. So if we have a look at this pyroxenite at the top, caliper we got a density of 2.49 or 5, and we got fairly similar with the vacuum pack or the paraffin wax. Slightly higher, I don't know why, with the paraffin wax. We've got a number of examples and generally pretty close. Then I did a competent unoxidized pyroxenite, and you can see they're all around about 3.3 with the exception of the cling wrap which went down. And we'll come back to that one a little bit further on. And then this is a couple of photos that Bill's given us. It's a really neat piece of equipment. It's from South America, I think, where they've taken the whole extent of core, meters of the stuff, standing up there. They've got cameras at the top. They can photograph it, and then drop the whole tray. The tray's got holes in it. Drop the whole tray into the water and measure the densities. Pretty neat, and I think that from what Bill's told me, they did every meter of core that way. Obviously, it was competent and they could do it. Half core. So what got Grant involved with this is I'm totally useless with math, so I said to we had this project now, and we were getting like 10, 6, 7%, 10% wrap compared with other methods. And what the people were thinking of doing was applying just a factor of 10% to everything. Wrap everything in cling wrap, and then add 10% onto all of it. I wasn't very... and the problem is that the cling wrap gives a bigger volume for the same mass, so the density goes down. And this was the problem. Once we started looking at the core, because we'd been given these sort of 20 or so pieces of core about that long, was the fact that when they were cut, not only did they have irregular ends, but also there was a ridge there. So as soon as you put cling wrap on, the air gets trapped. So what I did was ask them to trim that off and trim the ends wherever they could, and then we ran a series of tests. For example, there's a piece of so-called half core which was actually... And what we found was with the cling wrap, a density of 2.28 compared with 2.4, so the cling wrap was 6% on average, that bias over there. Not consistent, but always lower for the cling wrap than the caliper. And then if we just compare the we wax-coated 10 samples compared with the 18 of the others, and I think we got a fairly good match there. And finally, just something about the pycnometer. A lot of people say, oh, you can't use a pycnometer. Well, I've actually found it quite a useful tool for comparing, especially fresh, competent rock chromite mine. So all the pulverized samples we use to measure density. And this is just a pycnometer at Intertech here in Perth, where there's a sample chamber. And it uses, and that sample is put into a plastic vial, put into there, and this purely measures the volume of the sample based on the gas that's fed through the system. And just to give you an example, this is they were all like 100 meters deep or more, nice and fresh. The densities are 1, 2, 3, and 4 up there, so we went up to 4.5 for the really clean chromatite. And that's the Archimedes method. We used just unsealed Archimedes on the vertical axis, pycnometer there, and I think quite a good relationship between them. We've just got two populations because that's clean chromatite at the top, and that's chroniferous peroxide. And now I'll hand over to Grant.
Sorry, I'm struggling with this. Alright, thank you, Andy. So the correct calculation of is really important, as we all know. And first thing that I want to highlight is that a cylinder has some really interesting geometric properties that allow you to calculate the volume really easily just using a caliper. So we all know that a cylinder with planar ends, like you see at the first example there, with the planar ends cut at right angles to the axis or the length of the cylinder, you just need to measure the diameter and the height, and you can simply use those two to calculate using the standard formula for the volume of the cylinder. But what's really interesting with a cylinder is that as long as you have got a cut on the end of it, you can still calculate the volume quite easily using caliper measurements. And this just shows you here that, sorry about that. This just shows you that the volume that you lose over there is exactly equal to the volume that you gain there. And this is true for any angle of the planar cut at the end. So all you need to do is measure the center line distance, and you do that by, and this, you can have these angled planar cuts. You need to measure the shortest length and the longest length, average that, which gives you the center line length, and then the diameter, you get the radius from that, and then you apply your formula. And what's interesting about these three cylinders here is that they look quite different, but actually they are exactly the same volume. So now, the half core. It's never a half core. Part of the problem that we found. So we're often confronted with core samples that have nominally been cut in half. If the core was cut so that the section you need to measure is exactly half the core, it's really easy to calculate because it's just half the cylinder. But you need to remember that when you cut exactly down the center, the saw blade has a width, and that removes some material from the core. So this shape is mathematically referred to as a cylindrical section, and this end section that you need to measure to get the area for the volume calculation is the circle. So again, with a half core with perpendicular ends, when you cut using a 3mm blade on HQ core, you lose about 6% of the volume, and for NQ core, that volume loss is about 8%. And here's a practical example of that from where they had an NQ core, cut it very neatly, as you can see, almost exactly in half. But when you actually do the weights, you see that there was a loss of about 88 grams, which equates to around 8%. But you can still solve this problem quite easily, actually, and I think there's a well-known formula for doing it that you just need to be a little bit wary of. All you need to be able to calculate that end area is what's and the chord. And with those two, you can then calculate the radius, and with the radius, you can then calculate that area. With the height, you can then get the volume. And this, the formula that you use to calculate that is commonly used by architects. And another practical application of this is to calculate the volume of fluid that's left in a cylindrical tank. But the important thing with half core is that for this you need to have planar ends that are cut at right angles to the axis. Because if you don't, you end up with what's called a cylindrical wedge at the top there, and the mathematical problem becomes quite tricky, and the measurements also become quite tricky. So when you're dealing with a half core, and this is of course all relating to when you're using calipers to measure your core, for whatever reason you couldn't use an immersion method, and you need to measure. So just be very wary. You can solve that problem, but it does get rather tricky. So yeah, the caliper method is a really quite a quick and easy method to validate your water immersion methods, or you could, but it needs to be done correctly, and the potential errors that could lead to bias need to be understood. I think there's a slide missing here. Anyway, I think I'll just hand over to you, Bill. Okay, so there's just a slide here where I did a theoretical calculation to show you what happens when you assume that your half core. And I've just based it around a HQ core, where you're going to lose about 6% of your volume. If you now assume that you've got a half core and you just apply half pi r squared to get that area and multiply it by the height to get your volume, obviously you've got that 6% error built in there. So where you've got a case of a 20 centimeter piece of HQ core weighing about 800 grams, if you calculate it correctly by measuring the sagitta and the chord, get the area, do all the calculations properly, you would end up in that scenario with a density of 2.7. But if you assumed that it was a half core and you did a pi r squared on it, a density of 2.53. So now if you take a theoretical case of a 4 million cubic meter deposit and you then apply those densities, you get an incorrect density. 1 million tons compared to the tonnage of 10.1 million tons compared to the true tonnage of 10.8 million tons. And if you assume that that's an estimated grade of 3 grams per ton of gold, you end up with an incorrect 0.97 million ounces compared to a correct 1.04 million ounces. On that, at yesterday's gold price of 1,554 Aussie dollars to the ounce and a 90% recovery, say, you end up with an incorrect in situ value of, or expected revenue of $1.363 billion, sorry. Yes. $1.36 billion compared to $1.45 billion. So you've got $87 million of lost value right there, and that could be the difference between your investment decision or not. And so I'm just going to hand over to Bill for some concluding remarks.
Thank you. Yeah, look, it's a really interesting case study that Grant developed, and we apologise for the fact that the slide's gone west on that particular case. But look, our main points are really that mineral resources and ore reserve estimates rely on grade, volume and density for reporting tonnes. And note that in the JORC code you can actually report volumes or tonnes. There's a clause right at the start that says they're equivalent. You can decide what you want to report. For all, in all cases, if you want to talk about that or talk about volumes, you can do that. Just like you can talk about quality or grade. For density determination of representative samples, measuring the mass is easier than the volume. Understanding core volumes, what Grant's example was showing is that if you get this error of plus or of 8%, a bias of 8% in measuring the volume because it's not truly half core, and you the example, you end up losing on a $1 billion project, on a $1 billion project, you end up losing around $100 million or underestimating the project by $100 million worth of value. Make sure that the methods chosen for determining your dry bulk density are appropriate. That means you make sure that you're not trying to immerse potash core in water, for instance, and just wash away. Make sure that the methods that you're using are correct, so that you've got all the QA/QC procedures in place. Make sure everything is validated by using an alternative method. And that's why Grant and Andrew have put so much effort into talking about doing this caliper method correctly, because if you don't get it right, you absolutely get a bias. QA/QC for density should be noted in your public reports under JORC 2012. And the competent person, of course, should be able to defend the conversion of volumes to dry or wet tonnes, noting that all manganese projects now are being reported as wet tonnes. So thank you very much for your attention, and our team will be pleased to address any exciting questions you have about this stimulating topic.
Anyone? Questions?
Bill, how do you, with buggy material, and you use something like one of the wax methods, how do you accommodate? I'm not sure whether your bugs totally dry, how much air is in there, or how big the bug is.
Well, yeah, that's one of the advantages of using the caliper method if the core is sufficiently competent for that. Okay, but one of the points that I think came out of looking at the errors involved in this is use big samples. If you've got long lengths, there's much more chance of eliminating the errors that are due to the irregular distribution of the bugs, for instance, in the core. And all of the other intrinsic errors that accumulate, just errors in measuring the volume or errors in measuring the weight. If you use large samples, HQ is better than NQ, of course, but also long sticks of core. And we've seen some interesting examples. I know years ago at the Clio Sunrise Dam project, every metre of core had a density determination. The whole project was then, the resource estimation was done by treating the density just like the grade. Specifics of it, yeah, of course it's tricky, Sandy. That's the thing.
And just further to that, if you do have that sort of situation, how do you go with physical methods? I don't know whether you have that to do with it, because I certainly haven't. And I just wondered if we've got these bugs and we're not picking it up.
So I've always liked the wax method. It's got lots of interesting little things about it, like beeswax is always produced apparently at a very constant density, and it's quite technical. You have to do the density of the wax and measure the volume of the wax you've used. But if you make sure that you're, like if you were doing density determinations on the Anticuchin and Pesolite, there's bugs that come in on the surface. To make sure if you've got enough of it, or you use the large 8 inch, then you get representation of the bugs inside. So I like to seal up the core and prevent the movement across. For downhole density sampling is another interesting example where there's a change in the volume. The volume that you measure with your sonde, because it's looking outside the hole and going into the walls, can be much bigger than the volume of core that you actually get out of the ground. So again, you know, it's a great way to do it.
Something that Louw can touch on is the fact that you obviously have to dry the core before you do any of your measurements.
Yeah, look, we've skipped over a lot of the stuff that I used to get really excited about the wax method and all the different intricate steps. But you get your moisture by having the core as delivered out of the ground, and then dry it, and then do your volume determination. That's the point you're making. Because moisture is also critical, I think.
Yeah, it was mentioned, so trying to convert it to dry tunnel.
What do you consider as a long piece of core?
3 metres. Well, that stuff you saw, that was a really interesting little test rig that they had at Andina in Chile, and I think that was about 3 metres. Only confident, but they could do the whole thing, photograph it hyperspectral, and then weigh it dry, weigh it wet. Because when they weigh it dry, it's still a bit moisture in it, so there's an assumption.
It doesn't have to be continuous in 3 metres.
No.
Do you think the picnometer method is universally applicable for, say, a monitoring techniques you're using? I'm sort of wondering about how valid picnometer measurements might be if, say, the material that you're doing density measurements using other methods, buggy material will have a lot of internal porosity.
Then I wouldn't use it. I mean, if it's buggy.
So even as a second method, as a
So this gas picnometer method, which Andrew has used and
Yes.
showed, is interesting for determining the industrial minerals. You grind it up.
We did
Or
with
it's-
the chromite, we just used the
Oh, yeah.
samples with assay for chrome.
Okay.
And seeing as though they had the samples, it's a regular method, we included it, so we had all the data, but it was all fresh, competent, non-porous.
The classic picnometer.
Because, like I said, the samples have gone to the lab, they've been pulverised, and it's just something that can sort of work into your assays.
But
So the classic picnometer is used to determine SG G, because you've got a pulp, you put it in the triangular flask at the volume, and work out the volume of the material in the volumetric flask. And, and you don't have any porosity.
That's exactly right. So that's why I'm just wondering whether or not a relationship that can be used as a check on whatever other method, or if you've just totally destroyed it.
Personally, I'd rather not, because I have also done oxidised chromite and it doesn't work terribly well there. It's better to use the caliper method, I think, if you can. The caliper method is quite robust, really.
So using two methods in conjunction will give you a way to understand the porosity of the sample. Getting some excitement now. Oh, sorry. Come on, guys. Stand up.
Question for Bill. So, typical example for a resource geologist, you get a gold resource. They haven't done any density estimate.
Oh, none.
They've used an assumed density on typical eastern gold field.
2.0.
You've got to classify it. You've got to put it, everything else says it's indicated, so. But they've got no density. Where do you sit with the jaw code?
We have to look at what's the risk. You can try and get around it.
Well, it's pretty big from what you were saying.
By being,
8%,
well, yes,
10%.
You can be, it's got to be transparent, it's got to be material, it's got to be competent, independent, right? So you look at all those things and say, can I just make the statement that we've got all these drill holes, we've got these samples, but we don't have any measure of the density as such. We'll just take a guess at it. It's an exploration target, isn't it? Because you're going to declare the tonnes as plus or minus a certain range, even if you got the grade clearly defined. And now you've got a situation where you're saying we can show we've got continuity of geology and or grade, so we think it's indicated, but in terms of the rest of the substantiation, it's not even be inferred. It's no different to saying we've got all these assays, but we don't know who did them where, and we don't know what the machinery was that was done, and we don't have any QA/QC on it. Things about density. The reason it's so boring, of course, is because unlike gold, where the grade can vary from 0 to anything you like, density is only going to vary from somewhere just below 1 to somewhere around about 4, say. Now that means that the precision, the errors, you take enough samples and you do it well, the precision will all balance out really quickly. You get the central, the mean on your side, and it will all come in, you get nice Gaussian distributions. But if you've got a bias, you're dead. And it's really easy to get a bias, and probably easy to prove. Ivy, hello.
Hi. It's just a bit of a nightmare hypothetical. But if you were in a situation where you unfortunately only had RC drilling and you had to get a density of some sort, would you advocate mucking around with RC chips, doing downhole geophysics, demanding at least one core hole? What's a good strategy?
Yeah, look, I don't think you're in a situation to suddenly demand a drill hole, another drill hole, or a core hole. But I think you can get a fair bit of information from RC drill chips, comparable deposits nearby, but you've also got enough chip samples that you can. Depends what you think the assumption is in the ground in terms of vugginess and porosity. And it's going to be hard to get it right near surface because it's weathered, but it's always going to be hard to get it right near surface. And as you go down deeper, if you're in hard, competent rock and you've got RC chips, that's a much better representation.
You could use a technology then.
Yeah, you can use gas to sort of eliminate all those the chip behaviour.
Just with the caliper method, how many actual measurements down the core do you measure with the caliper?
Well, we would advocate probably taking, 3, sets of 3 so that you can get an average. Well, you're usually looking at a smallish piece at 20 centimetres. So, yeah, you'd want to take a couple of measurements, probably 3, just to get an average. I mean, You hopefully you get it right. And of course,
The more the better, I think. Right? The longer the piece
That's
is,
true.
the better.
The longer the piece is called, the more measurement.
Yeah.
And can't you validate it by just looking at what's the advantage of taking a few more measurements? But
and really you're going to validate if it's full core, what you're going to end up doing is validating if you've got a real cylinder or not. With measurements and making sure that it is nice and flat, which it probably isn't.
There's some simple
One thing
take
we
homes
didn't
from
mention was also is to actually do the density measurements early on in the project, destroy the samples.
and do them on the whole core if you possibly can, right? And big RC chips if you've got these chips. I think.
Are there any other liquids you use other than water? Because sometimes you got rock, and once you put it into the water, it swells, so you get a difference anyway.
I've heard of that. Why not?
No, you can use
Kerosene.
kerosene. I've done that with industrial. No, it's not industrial. It was only the bitumen and some of the
Kerosene, did you say?
Some
That's,
industrial.
I mean, I have never seen it, but I remember hearing about it.
with kerosene.
Why? Something that won't denature the core. I've got a feeling that they do something like that with potash too,
Yeah.
because the potash dissolves. Chris, mining.
The sequence has been really interesting because, as has been pointed out by everyone tonight, the whole thing above density has been roundly misunderstood for a very long time. The only other term that is used very poorly is the conversation between the geologist and the metallurgist, where the metallurgist says, "Is this sample representative?"
Yes.
And the geologist says, "Of course it is." Now, but getting back, a company that both you and I work for, they measured and calculated bulk density incorrectly for 20 years. They were totally consistent in their wrongness all the way on, because they'd never heard of Archimedes, and they just did it wrong. So I would beg you to question where any project you go to. One of the first things to do is get them to show you how they measure, how they think they're measuring density. Because it's the blindingly obvious, it's easy to see, but if they're getting it wrong because they didn't do physics in high school, they'll get it wrong and they'll just keep on getting it wrong.
I think the point you're making really is interesting because Andrew and I assume we've sorted this out. Everybody else here with a bit of grey hair sorted it out, so it's all done now. Right? But people come back and they start again and they reinvent it for themselves and they do it in a new way, and we see that. And because of the change in the mineral industry, because of the cyclical nature, we're always losing good people.
So could you have another evening's talk on that line conversation?
So what is a representative sample?
About that, yeah, because there's so many mills which have been built all around the world, which have been built for the average material. And by the way, you can't put all your 20 years material through the mill in the first month.
These are really tricky problems, and I've made a career out of taking really complicated ideas and simple statements, and everybody afterwards says there's nothing hard about that. That's all right.
I was just going to say, you mentioned somebody did it for 20 years. The particular company I mentioned, that big foot thing, has been doing it for 80 years and they're still doing it. They sell $1 billion worth of clay a year. They always get out more than they thought was there, which is really nice. So it means they get all the geology wrong and it still works. It looks like.
I guess the thing is, if you're going to be wrong, you might as well be consistently wrong.
Yes, which way was your example wrong? Too low or too high?
It was because they didn't zero the planet. They never zeroed the planet.
Good.
Anyway.
We've got one last question.
Yeah, I've got one. Just is there any new technology that's coming out with a lot of the optical sensors and imaging technology that you can just throw a bit of core, get the machine and optically tells you what its volume is?
Probably yes.
Yeah, it's like those things they use for on CSI and all those Rizzo programs where they put a skull on a thing and they cerebral tape and take Brazilian.
You'll still have a problem with porous samples though. That's a very good idea, I must say, but I think porous samples will still be an interesting one.
Interesting, because, using the same concept as the laser scan eyesight or whatever it's called, mathematics eyesight or any of those sorts of things, and you've seen them, they set them up in a room and they can take a picture of the whole room with everybody's faces, everyone's recognisable. There's no reason why you can't scan something like that to create, for instance, a 3D printed model.
Yeah.
Reverse the technology, and then put the perfect drill core cylinder around it, and then you would be able to account for the bugs as well. But most of we can come up with ideal solutions for all these problems, but then the poor geologist in the fields, with the heat and the flies, and he's presented with this rubbishy piece of core that he's got to work with, and that's when it gets tough. So, being transparent, disclosing, these are the problems. These are the potential sources of errors, plus or minus this. This is the way to go. This is potential impacts on your ore reserve. This is what's happening in your grade control. All that stuff's important.
That was a good point about measuring the volume.
Can I just make one comment here? I walked up to a place up in the Pilbara where they were doing density measurements, and whenever the fluid evaporated, you just put in more water and more water. So they're actually measuring hypersaline water.
And a high temperature, which also messes up the density too.
Well, I saw a really good similar case actually, Adrian, where they were trying to do the wax immersion method, but they didn't have enough heat in the little bowl, or they didn't have enough wax, so they're putting the samples in, but they weren't getting wax all over the sample, letting it cool and dry, and it all looked good, and they put it in water, and they'd do the density, and they'd do another one, and they started plotting graphs showing with this particular rock the density increased over time. Rock it after 15 minutes, it's a lot more dense. What was happening is water was seeping through the wax or getting through the gaps in the wax. The water level was going down, so the volume was increased, but the volume.
I think an interesting point that maybe we didn't highlight enough as well is on the when you're doing Archimedes, you should have a standard piece of core that you're using to calibrate yourself the whole time as a QA, just to make sure that you can see any biases creeping in for heat or hypersalinity or whatever.
I think the salinity thing in the water is important. Temperature, and I don't know whether pressure, does it make any difference if you're at high altitude?
Yes, it does. Yes, it does. Don't do that to diamonds. It will cost you a lot of money.
I really enjoyed these questions tonight. It's, as Heidi said right at the start, it's all part of the good science, bringing out lots of different ideas.
The question I've got for you is very in that we don't get the core from what we're currently doing, although we may down the track, but our ore body is kimberlite. So it's basically going to be a 6.6 to 6.5, or in our case, going to be 2.55 to 2.65. So that is a global number. I'm just wondering, in terms of what we're currently doing, getting chip samples and ore body samples from basically got a bit of kimberlite from surface. How much variance do you expect us to get across a known sequence? So in terms of what we're doing.
So you're dying the core?
No, we're not. We've just done small 4 or 6 inch drill holes at the moment, just to outline the ore body.
Well, you take enough samples and you look at the variability.
No,
the densities won't be set surely.
Yeah.
And when you get down, they'll be much higher densities. But
Don't worry, Bill, I'm working with him, so I'll make him.
All right, I think we're starting to get some people to leave, so we'll call it in. There's the bars open upstairs.